There's a second part of problem 313. It asks us to use the given fixed point iteration update equations and starting again at x1 and y1 to carry out the first 5 update iterations of this system of equations. I went ahead and put those update equations into MATLAB. So notice here I've defined those as x next and y next, just pretty much as given straight from the book. And I've had to play a little bit of variable switch-aroo because I had a problem. Initially, let me actually go back and reproduce my mistake. xi, yi. It was actually a mistake that helped it converge a bit faster, but that was a bit odd. So if I go ahead and run this, you'll see that it actually does seem to be converging. It goes x, y, x, y, x, y, update, update, update. 282, 213, 303. So really, if you just look at the x's, every other entry, it's getting smaller. It's converging obviously to about 3. It seems like the y entry is converging to about 2, which matches the Newtonian solution we got. So that means it's working correctly. It is converging. But this didn't match hand calculations for the problem. The y solution was always one step ahead of where the hand calculations were. It's like somehow I was magically skipping an iteration. So I was thinking, I was like, what's going on? Why is this a problem? And I realized that the way I had programmed this, I was overriding x of I that I was using in the y equation before I should have. So once it executed line 6, x of I that line 7 was using was already updated. So that's why essentially the y of I value is always ahead of my hand calculation. So now I just did kind of this substitution. Instead of saving the variable as x of I save it as x of next. So that way I can complete all of the step iterations for every function. In this case, there's only 2, but perhaps there would have been 6 or 7. And so that way you can complete that iteration's calculations with only that iteration's set of data. You delay the assignment of the new data to the state variables until the very end. So after do this reassignment exercise, it's fine. So now if we run this, you see that the solution still converges to the exact same answer, but thankfully it follows much more precisely the handwritten expectations. As you see, this isn't exactly converged as far as we'd like, so the typical thing, crank that number up, tell MATLAB to go for it, and you find that it converges very nicely down to 3 and 2, nearly identically, so close that MATLAB just went ahead and rounded it off straight at those values. It still only took a fraction of a second. So in a way, you might say, why don't we just use fixed point iteration all the time for multidimensional solutions? That was way easier. You just write down the equation, set up the system, it iterates and updates, it's fine. It's a stability question that holds it back. This is a homework problem out of a textbook, and it works very, very nicely. They gave you the form of the nonlinear equations in a form that's rearranged, that is stable. They gave you the initial points that make it work. In real-world applications, that may not always be as reliable. So knowing these other, granted more complex, methods allows you to be more functional in the real world without having to be spoon-fed the starting point and the equations and everything else by a homework problem. So simple for an assignment, more challenging in real life. That's why we teach you very different ways, different advantages to different problems.